start with this one. This is W17 and question paper 2-3. So starting with the first question, what is bond energy? Bond energy is it's the energy that is needed to break a bond, 1 mole of bonds in gaseous molecules. So needed to break 1 mole of bonds of the same type. And in gaseous molecules. And use data to calculate the NH bond energy. You must show your working. So what is happening over here? You're breaking a bunch of bonds. So you're breaking how many bonds? It's bonds broken, which is endothermic, and bonds formed, which is exothermic, hence the minus sign. And that is equal to the enthalpy change of the reaction. So the enthalpy change is already given, that's minus 92. The N, how many bonds are broken? N triple bond N is broken. So that is one of them. One of this bond is broken, and that is endothermic. And 3 HH bonds are broken, so that is also endothermic. And how many bonds are formed in NH3? There are 3 NH bonds. So over here you have 6 NH bonds that are getting formed, and the sum would be equal to minus 92. So you need the data booklet for this.
Why, sir? Why would you need the data booklet?
I just saw you the bond energies are given. I didn't see that. Okay, so the bond energies are given. So that's 944 plus 3 HS, that's 436 into 3. I think we calculate, what do you get for this? The NH bond energy is not given. Is equal to minus 92. So what do you get for NH? Can anyone solve this?
C90.
Take a C90. That is probably going to be correct. So that you're getting C90 for this. And remember, bond energy is always endothermic. It's always going to be a positive value. So if you get a negative value, I mean, this thing is always positive. So that means you've messed up the signs somewhere. The next part is Boltzmann distribution. So the Haber process is usually carried out at temperature of, so you have got a Boltzmann distribution. Using the same axis, sketch a second curve to indicate the Boltzmann distribution at a higher temperature. So at a higher temperature, you'll have more particles. So it's going to rise over here and it's going to fall at the lower temperature side, lower energy side. So one second. Okay, so the curve would become like this. And it would become flatter as well. With reference to the Boltzmann distribution, state and explain the effect of increasing temperature on the rate of production of ammonia. So this particular question is about rate, not about equilibrium. So what happens to the rate? You're going to state that molecules having energy greater than the activation energy or the minimum energy required for the reaction, they were very few initially. You had very few particles having high energy. So there were fewer successful collisions. And now at a higher temperature, the number of particles at higher energy, that they've increased. So you've got more particles that can successfully collide with sufficient force. So that is what you're going to write. So explain the effect of increasing temperature. So higher temperature. So you've got more particles having energy greater than greater than activation energy. So you get more frequent and successful collisions. Anyways, moving to the next part, Stan explained the effect of increasing temperature on the yield. Now, when he talks about yield, that's equilibrium. Okay, so make sure, is he talking about equilibrium or is he talking about rate? In the first part, he was talking about the speed of the reaction. Now he's talking about the yield of the reaction. So, and you're going to use the Lee-Shatler principle. So when you increase temperature, which one is favored, endo or exo?
Endo.
So the endothermic is going to be favored, which in this particular case is the backward reaction. So endothermic, like over here, the forward is exothermic. So it's going to go in the, and the yield is going to decrease. So backward is going to be favored and your yield decreases. Okay, then you have the next one. You've got at a pressure of 2 into 1 mole of this and 3 moles of hydrogen. The final equilibrium mixture formed contained 0.3 moles of NH3. Calculate the amount in moles of N2 and H2. So this is an equilibrium question. So this is, you need to make a table for this. This is about Kp. The question is about Kp. So this is the reaction. What are your initial moles? So initial moles are 1 mole of N2. So that's 1 mole. And there is 3 moles of hydrogen. They're mixed together. And that's it. So there is 0 moles of NH3. And then at equilibrium, you've got, they say that there's 0.3 moles of NH3 present. So you have to find the moles of the other substances. So if you have 0 moles initially, and now you've got 0.3, so how much NH3 has been produced in the reaction? That's going to be 0.3, right? So that means 0.3 moles of NH3 has been produced because you had 0 initially and now we've got 0.3. So okay, if you want to produce 0.3, I mean, as you can see that 0.3 have gotten produced. So how much N2 and how much H2 must have reacted for that? Okay, if you want to produce 0.3 moles of NH3, so how much N2 and how much H2? How much?
0.15.
0.15 of N2 would have reacted, right?
Yeah. And then I think 0.45.
You can 0.45 of this would have reacted according to the ratio. 2:3 and 2:1. And most of your answers are, I think, correct. So what's left? 1 mole, you started with 1 mole, your 0.15 are gone. So you're left with 0.85. 3 moles of H2 and now 0.45 have reacted out of that. So that's 2.55 moles, right? So those are your equilibrium moles. Is that clear? And you can fill that up. And then they ask them calculate the partial pressure of ammonia in the equilibrium mixture, give you answer to 3 significant figures. So partial pressure of ammonia, these are your equilibrium moles. So partial pressures of ammonia would be the mole fraction of ammonia, which is 0.3, divided by the total. What's the total? It's what do you get? What's the total number of moles? What's 0.3 plus 2.55 plus 0.85?
3.7.
Okay, so out of 3.7 moles at equilibrium, 0.3 moles belong to ammonia. So that's the mole fraction into the total pressure, which is 2 into 10⁻⁷. and that will give you your answer. What's the answer? And it has to be accurate up till 3 significant figures. So give your answers to 3 significant. यहाँ पे बल्कि उसने they've written it. Kiara, what's the partial pressure?
Um, 1.62 times 10 to the power 6.
ठीक है, times 10 power 6 pascals. And then in this question, they've given you the, I mean, this one is easy. They've already given you the partial pressures of another equilibrium. So product concentration, pH3, that's going to be squared. And you're going to be dividing that by Pn2 into the pressure due to H2, and that's going to be cubed. So try finding this one. And it's not that easy. I mean, you would struggle with your calculators. Make sure you use your calculators properly. I mean, everything is the same. You just have to put all of this here and tell me what is the answer that you're getting. Make sure to use brackets as much as possible on your calculator for this. So we're getting 1.1. Somebody checks this 1.1 into 10 to the minus 16. And again, 3 significant figures, make sure. I mean, I didn't. What's the third one? It's 1.10. So this one, did anyone else get this? Let me just check with the marking scheme as well. 1 second. So this one is, it's 1.00 into 10 to the minus 16. I'm not sure why. I mean, the market scheme, it's 1.00. So not sure where the error is, but that's the answer. If we've copied the values properly, that's 9.62, that's 1.40. Try doing this again, see if you can get 1.00.
Yes, sir.
ठीक है. As a next one, ठीक. As a next one, calculate the value of Kp for this. Calculate the value of Kp. We did that. What I said, they were looking for the expression for Kp. So we calculate the Kp, you find the units. So units is easy. That says Pascal squared divided by Pascals into Pascals cubed. And that's going to give you, I think, Pascals to the power minus 2. So that's going to be a unit. Okay. The next one is the reaction is repeated using the same starting amounts of nitrogen and hydrogen. The same temperature is used, but the container has a smaller volume. State the effects, if any, of this change on the yield of ammonia and on the value of Kp. So first thing, Kp changes. What thing changes Kp? The value of Kp. There's only one thing that changes the value of Kp. What is that?
The amount of moles on it.
The value of
Pressure,
Kp,
sir.
not pressure. Value of Kp
Temperature.
is a constant and it only changes with temperature. Okay? All equilibrium constants, whether it's Kp or Kc, they only temperature changes it. Otherwise, this ratio remains a constant. Product over reactant ratio remains a constant. So he's saying the same starting amounts of and the same temperature is used. So if the same temperature is used, effect on the value of Kp, there's going to be no change, right? Okay, no matter what you do, the Kp value will not change. The other part is, if you use a smaller volume, where would the equilibrium shift? I mean, where would this equilibrium? I mean, everything, all the conditions are the same except that a smaller volume is used. So if you use a smaller volume, where would the equilibrium shift? No, it's what do you mean by smaller volume? First thing, we need to interpret this that if you use a smaller volume, so you're basically using a higher pressure. Volume and pressure. So when you increase pressure, which side is favored? The less gas mole side is favored, according to the Lee-Shatler principle. So the less gas side is the forward side. It's got 2 moles. So hence the ammonia yield would increase. So it increases. That's it. No explanation needed for that. Just 1 mark question for the 1 mark answer. And remember this thing, like the other ways of stating what is meant by higher pressure. You decrease the volume. Now this one is about this is period 3 ionization energies. Before that there is sodium. I mean, we can add that as well. And after that it's chlorine and argon. So that's period 3. Explain why there's a general increase in the first ionization energy across the period. So what happens across the period? What are the 2 points? Number 1, why do the ionization energies increase across the period? Okay, because the number of protons, nuclear charge increases. So you got more protons, more nuclear charge. Any other factor apart from that?
Similar shielding.
Okay, so same shielding.
So if this shielding is the same, doesn't that mean that doesn't it go against?
Which one?
It doesn't. Shielding.
It doesn't. I mean, it's not a point as such, because same shielding means that it's not playing any role.
It's constant, right? Yeah.
Yeah, it's constant, right? Distance.
Slightly. Distance doesn't. Isn't it because of the more protons?
Yes. So the distance slightly decreases. So you got more attraction. But they're probably going to give you marks for more protons only. But there's one thing that has to be always written at the end. And what is that when you get a ionization energy question?
Greater attraction between the outer electrons of nucleus.
Okay, so there's going to be one separate mark. And that would be, see, I just checked the marks. The similar shielding is 1 mark in this case. So okay, they just called this proton and shielding. That's 1 mark. This whole thing. Distance, no marks given for that, and but 1 mark for that statement. At the end, always write this statement. So because of all of this, there is greater attraction. So because of all of this, there's greater attraction between nucleus and outer electrons. So make sure you always write this statement at the end. As the next one, sketch on the graph the position of the 2 elements that come before Mg in this sequence. So I said, this is sodium. Now before this, there's neon. Where do you think neon is? Like the period ends over here. So where is neon? What's the next one? It's going to be very high, because so neon would be somewhere at this point. Because that's in the previous period. That's a smaller atom that's got lesser shells. The electron is much closer to the nucleus, so there's a lot more attraction, more difficult to remove electrons. Explain why reference to electron arrangements, the increase in first ionization energy between Mg and Al. So Mg and Al, so why is there a dip? What's the explanation for this? I mean, you have to explain.
The electron is in a p orbital for Al.
So Al electron is removed from a higher energy
p orbital.
Higher energy 3p orbital. 3p. 1 second. Which is more shielded as well. So Al basically has more orbitals. And so it's removed from a higher energy 3p orbital. And while in Mg, you'll write about Mg as well, that the electron is removed from a slightly lower energy 3s orbital, which is less shielded. So you can write the other one as well. What about P and S? Why is there a dip at group 6?
Because I think oxygen, sulfur will have the spin pair repulsion.
Okay, so first thing you're going to describe is that you're going to describe the orbitals first. That's 1 mark. Phosphorus, the orbitals are all half filled. I mean, in phosphorus, the p orbital is half filled. It's half filled, so each orbital p subshell basically is half filled. So that is phosphorus. While in sulfur, the p subshell is paired because it's got 4 electrons. So there is spin pair repulsion, or the electrons repel each other, spin pair repulsion. So that's why it's easier to remove electrons. So always describe the orbitals first and then describe the reason. Now the next one is the chlorides of element in the third period behave in different ways when added to water depending on the structure and bonding. L and M are each a chloride of an element of period 3. And they are studied. L is a white crystalline solid with a melting point of 987 kelvins. Is this an ionic chloride or a covalent chloride? L. I mean, it's got a high melting point, so it's probably going to be, and it's crystalline as well. So it's not covalent, it's probably ionic. And it dissolves in water to form an approximately neutral solution. So that is sufficient to figure out what L is. Which chloride is neutral?
NaCl, sir.
Okay, there's only one, that's NaCl. So that is NaCl, and addition of NaOH to an aqueous solution produces the NaCl is completely neutral, but over here they're saying it's approximately neutral. Who's approximately neutral? Okay, there's a first.
MgCl, sir.
The other one is MgCl2. MgCl2 has very slight hydrolysis. It has very, very slight hydrolysis. The reason I'm getting rid of NaCl is कि यहाँ तक तो it makes sense that NaCl would work, but after that, addition of NaOH to an aqueous solution of L produces a white precipitate. That will not happen with NaCl because all Na compounds, group 1 compounds, are soluble, and that precipitate will form with, if I add NaOH to MgCl2. So in my beaker, I'll have all these ions. MgCl2 is soluble, so Mg plus 2 ions and Cl ions, and Na plus 1 is next to it. So it's going to have Na plus 1 and OH ions. They're going to form a precipitate. What is that insoluble precipitate that's going to be formed if I mix MgCl2 with NaOH? It's going to be magnesium. Okay, so that would result in the precipitate that's going to be formed, MgOH2. That's going to be a solid because that's not very soluble. The other thing that's going to remain in the solution is going to be NaCl. That's going to be aqueous. So So this other thing will happen with NaOH. It's going to form a precipitate. So that's going to be MgCl2. And MgCl2 is approximately neutral because it undergoes hydrolysis with water, but very slight hydrolysis. Like some of the Mg ions will attract the water molecules and will attract the OH ions, and they will form MgOH2 solid and will release H+1 ions. So there's going to be some hydrolysis because if you mix it in water. So people can यहाँ पे, ठीक है, let me just open the this one. We'll just go through all the hydrolysis of chlorides very quickly. So now the hydrolysis of chlorides, you've got this one. Okay, so remember NaCl is completely neutral. MgCl2 some hydrolysis. Why does it hydrolyze? Because Mg has a very strong +2 charge. So what happens is that it attracts the water molecules very strongly when you mix it in water. And it attracts the water molecules and repels the H in the water, and the H+1, they get knocked out. So that results in the formation of HCl or H+1 ions in the solution. So MgCl2 has very, very slight hydrolysis, and the pH is approximately 6.5 or something that's very close to 7. AlCl3 has a very vigorous, strong hydrolysis because Al, on the other hand, when AlCl3 gets mixed in water, Al+3 has a very strong attraction for water molecules, and it has a very strong repulsion for the positive H in the water molecule. So what happens is aluminium forms this complex and it starts knocking out the H+1 ions in the water molecules. So, I mean, this is hydrolysis. Remember, all chlorides reactions are hydrolysis. They're basically reactions with water. I mean, it's a reaction with water where water reacts with MgCl2 and AlCl3. And the AlCl3, which is a covalent molecule, no longer, it mixes with water, it reacts with water, and a new compound is formed. So all chlorides, Na doesn't hydrolyze, the first one doesn't. The first one only dissolves. And it's kind of, it has the same reason why, because there is no hydrolysis, only dissolves. Because Na+1 doesn't really attract water molecule because it's got a very small positive charge. So it doesn't really attract water molecules, and it doesn't repel the H positive as well. So the water molecule remains intact, and there's hardly any reaction taking place when you mix Na. So remember the hydrolysis, and the hydrolysis becomes more vigorous when you go down the group. PCl3, PCl5, SiCl4, they've got very strong hydrolysis, and you see fumes of the reaction is hydrolysis. Like any reaction, all of these reactions, like MgCl2, AlCl3, SiCl4, it's all hydrolysis. For MgCl2, remember, it's. I mean, you can say that it mostly dissolves. There's very slight hydrolysis. Okay, so just remember the term hydrolysis. The first one is dissolves. The second one is mostly dissolves, very slight hydrolysis. The third, fourth, fifth, and that's vigorous hydrolysis. You see fumes of HCl forming in the reaction. So anyways, where's the question? Where's the paper? So M, what is M? M is a liquid. So that kind of clearly indicates it's a covalent molecule. So first thing, which one is a liquid? There's one that is a liquid, and that's SiCl4. It's a colorless liquid. AlCl3 is a white solid. PCl3 is also a colorless liquid, so that's also a possibility. PCl5 is an unstable white solid. So you've got two options. SiCl4, you've got PCl3. These two options. So those are the only two. And PCl3. It hydrolyzes rapidly by cold water to form a strongly acidic solution, a white solid, and white fumes. Now, PCl3 does not do that. It doesn't form a white solid. SiCl4 does. Like if you look at SiCl4 is going to react and it will form silicon hydroxide, which is a white solid. While PCl3 is going to produce two acids. One is phosphorus acid, the other one is HCl. So no solids getting produced over here. So that indicates that it's SiCl4. And you have to explain the observation. So you're gonna write every point and you're gonna explain that. High melting point, that's ionic. Low melting point, so that's equivalent, and it's SiCl4 or PCl3 because they are liquids. They rapidly react with cold water, they form a white solid, so that means it's going to be SiCl4. You can write the equation as well. They're actually asking for the equation as well. So you have to give equations in this case as well. You just have to explain everything that we just talked about. Now, the next one is organic. So let me. So the next one is organic. So let's quickly go through this. First thing, halogenoalkane. I'll just do everything. They're talking about the type of reaction, the reagents and conditions for each one of them. So we're going to do this over here. So Br getting substituted by OH. What is this reaction called? I mean, what is the conditions for this reaction? The Br gets replaced by OH. So and where's my do you remember halogenoalkanes turning into that's NaOH? This is it. So that's NaOH aqueous and reflux. It's this one. A halogenoalkane, you have three substitution reactions. You've got you can replace it by OH ion, Cn-1 or NH3. You need to know the mechanisms for this. That's nucleophilic substitution. You've got SN2 mechanisms where the OH ion, NH3 or Cn-1 they come in the form of transition state and the Cl gets knocked out. Or it's for tertiary halogenoalkane, it's an SN1 mechanism where the Cl gets knocked out first and the nucleophile comes in later. So this particular reaction is NaOH aqueous and reflux. Okay, so it's just the chart. You just have to remember the chart. And this one is SN2. This is nucleophilic substitution, but it's a primary halogenoalkane, so it's a SN2 mechanism. They just wanted to know that it's a substitution mechanism, so that's it. How do you convert an alcohol, primary alcohol, to an aldehyde and then to a carboxylic acid? So what are reaction 5 and reaction 6, and what are the conditions for that? Yeah, I mean, you can do that with the K2Cr2O7. Acidified and reflux, and it will turn into, it's going to turn into an aldehyde.
So would KMNO4 be wrong?
KMNO4 would be right as well. Reflux would actually be wrong because I think he wants you to stop at aldehyde. So how do you stop at aldehyde? Distillation. So if you want to stop at aldehyde, it's going to be distillation.
Sir,
Yes.
if you just added Cr2O7 acidified, that would make no reaction, or would that still...
the K doesn't do anything. So I mean, the K is just a spectrum.
Oh, that's fine.
You could have sodium in place of K as well. As I distilled.
No, if it's just Cr2O7.
I mean, you can write that would be fine as well. Like if you just write Cr2O7 2 minus 1. As anyways, the other one, aldehydes to carboxylic acid, you got three things work for that. I mean, you can use the same thing, same reagents, or you can also use Tollens or Felling as well. So that is also going to work, and that's also oxidation. What is this one? Br turning into Cn. That's the same. Getting replaced by, that's again NaCN ethanolic. I mean, it's this one. We just did that. That you can replace the halogen with the OH or with the Cn-1. So you need NaCN ethanolic for that. Okay, that's nucleophilic substitution as well. And that is SN2 to be specific. So NaCN ethanolic and reflux. And that is substitution, nucleophilic substitution, SN2. The same one as this one, the same mechanism. How do you turn a CN into carboxylic acid? What do you do for that?
Acid hydrolysis.
Okay, so you're going to hydrolyze that. You're going to react it with a dilute acid, H2SO4 or HCl. So it's this part, CN turning into carboxylic acid, so H2SO4 and reflux. Don't use alkaline hydrolysis because that would result in the formation of not a carboxylic acid, but a salt of the carboxylic acid. So they're looking for carboxylic acid. So that's dilute acid plus reflux. And that is hydrolysis. There is hydrolysis. And what about reaction number 2? What is reaction number 2? That's halogenoalkane turning back into an alkene. So how do you do that? So that one is elimination.
Reducing maybe?
No, that's elimination.
Oh.
That's this one. That's the same condition anyway, but it's ethanolic and heat. It's this one. Like if you want a halogenoalkane and you want to turn it back into an alkene, that's NaOH concentrated, ethanolic, and heat. Okay, so if you use NaOH aqueous, you get substitution. If you use NaOH ethanolic, you get elimination. You get alkenes. So that is NaOH ethanolic concentrated plus heat. So that's this one, and over here they're looking for the mechanism now, SN2 mechanism for this. So we just saw that, and we want to form. So he's saying include necessary. You just have to make the starting point. So SN2 is, this is positive, this is slight negative. You got an OH -1 nucleophile, and its electrons are going to be attracted, and the electrons over here are going to be repelled. So that's basically your starting point. So make sure you the H2SO4 over here, this one. What's the question? When is H2SO4 used? What's the, in what context are we talking about? It's you can use H2SO4 over here, like dilute HCl, you can use dilute H2SO4 as well. Like hydrolysis of nitriles, you can use H2SO4. That's going to work as well. So so we're done with this table. We're done with this as well. Define the term structural isomer and name 3 different types of structure. So structural isomer is same molecular formula, different structural formula. I mean, it's molecule. I mean, write the whole thing. Molecules having same molecular formula, different structural formula. So the atoms are arranged or bonded differently. Types of, what are the 3 types of structural isomers? Okay, so it's chain, functional group, and positional, right? You can change the position, you can change the carbon chain, you can change the functional group, like esters and carboxylic acids are isomers of each other. So next one is 2-bromo-2-methyl propane is treated with the same reagents. Identify the mechanism. That's a tertiary halogenoalkane. That's propane. And bromine is on the second one, and methyl is also on the second one. So that's a tertiary halogenoalkane. So in this case, the mechanism is SN1. Why? Because the Br is going to take away the electrons first. It will form a carbocation. You can add in the H's yourself. So the Br -1 leaves, and then the nucleophile comes in later on. So what's the explanation for this? Why does it form a carbocation? I mean, what's the reason for? It's just a one line reasoning. Why don't you get a carbocation over here? Why do both things happen simultaneously? Like the Cl is getting knocked out and the OH is coming in. Over here, the Cl gets knocked out first and then the OH ion comes in. So what's the reason for that?
Because it isn't stable.
Because it's a very stable carbocation because it's got more alkyl chains. So the carbon, the Cl can easily take away electrons from it because this carbon becomes electron deficient, but it can get electrons from other places. So you're going to write this. This is the reasoning that carbocations with more alkyl chains are more stable because they've got more electron donating alkyl chains. So that's just a simple 1-mark reasoning. So carbocation with more alkyl chains, which are electron donating, are more stable due to lesser charge density. That's it. Don't mention about the space. Although space is also a factor because the OH ion cannot attack from any side because there's no space. The carbon is surrounded by large groups. But don't mention space. It's not in the marking scheme. It's the only reasoning is it's pretty hard to form a carbocation over here because the positive charge is really large. So the Cl it's very hard for the Cl to take away the electrons because the carbon positive is very strong. It's a very unstable carbocation. Over here, the carbon positive is has a very low charge density because of the electron donating alkyl chain. So just a 3-mark, two-line reasoning. That's it. So let's continue. I'm not really sure how much is left, but let's continue next time then. Okay.
All right.
I
Allow.
think actually this we can sort of finish this just very quickly. I'll just go over this. This is three marks. Explain the meaning of the term stereoisomer. So it's what is the stereoisomer? What definition? Like we did structural isomer. What's the definition of stereo?
Molecules which can't be superimposed on each other.
No, but the definition is same molecular formula, same structural formula. But so remember stereoisomers, they have the same molecular formula and the same exact structural formula, but they have different 3-dimensional. The molecule has a different 3-dimensional shape. Okay, is that clear?
Yes. Sir.
Yeah.
Achha, and even let me check the. Let me just have a check. The stereo that covers both. So the same one. It's the same definition in the MS as well. Yeah, different geometry in space. I mean, basically same molecular formula, same structural formula, and you can use other words to describe this. That they have different 3-dimensional shape, or a different geometry in space, or different orientation of bonds in the 3-dimension in space. So all of those words can be used to describe that. So but the molecules have different 3-dimensional space or 3D geometry. Give 2 reasons why but1e does not show stereoisomerism, because it doesn't have a chiral center, but1e, right? So you're going to describe that there is no chiral center. There's no carbon which is bonded to 4 different groups. Plus, the double bonded carbon atom is bonded to same groups. So it won't show geometric isomers as well. And you're being asked to tell about X and Y. So HCl is going to
Say
react.
2 reasons. So just say it doesn't have a chiral center, and second one would be.
And you're going to describe what a chiral center is. There's no chiral center, a carbon atom that is bonded to 4 different groups. And the double bonded carbon atom is bonded to same groups.
Okay.
I mean, so it won't show cis-trans isomers as well. And you've got HCl. So what are the 2 things that are going to be produced? Either the H. Actually, which side will the H bond with? Like if you're adding HCl to but1e.
The one with more
The left.
H's.
Take the right side, right? So that's going to be your major product. And then there's going to be the other one. That's going to be your minor product, right? Which one would, I mean, this one, the double bond would go away. This is the one that will show stereoisomers. What type of stereoisomers will it show? I mean, this is going to be X. So what is the type of stereoisomers that's going to be?
Positional.
Then it's going to be optical isomers. It's going to be, it has a chiral center now. Again, they're talking about stereoisomers.
Oh,
Yeah,
yeah.
the other one will not, because if the positions are switched, then it's not going to show optical isomers. Name the type, so that's optical, and use the conventional representation. So just draw the 3-dimensional shape of this molecule, like draw the chiral carbon atom, 3-dimensional, and it's going to have CH3 on one side, and it's going to have Cl. It's going to have CH3, CH2, CH2, and CH3. and I think at the top there's an H. So you're going to draw the mirrored version of this thing. Okay, so that completes the paper. So here, let's continue tomorrow then.
Sir,
All right, sir.
I
Allah Hafiz.
wanted to request you to send the notes in the A2 group.
ठीक है वो मैं ना I'll send them. I'll send them. वो
And,
I'll
sir-
send board. Should I send the board link? क्योंकि they're not
Yes, sir.
in the PDF form. So मैं send
And
करता हूँ.
sir, one more thing. Organic chemistry notes are also not completed. Like you haven't said, sent the third part, the polymerization and carboxylic acid and
अच्छा
derivatives.
ठीक है वो that's also a board. It's not a PDF. So I'll send the board link for that. ठीक है.
Yes, sir. Thank you.
चलो, okay.